So students, welcome to video class 33. We are continuing our discussion on the Bode plot for higher order factors, which is part 2. And in this video, we are going to deal with a special case. In the previous video, we have been doing a problem, say, where we have dealt with the higher order factor of the form s plus 2 the whole squared. We have obtained the asymptotic Bode plot and made the necessary correction. As I told you, for higher order for factors, this correction is an important aspect. Now we have also have two more sub questions which we will be doing in later in any one of our live classes. Okay, hopefully. So now, coming to this again, we are going to deal with a special case where we are going to consider a second order factor. So you might be wondering, this is also a second order factor, right? S plus 2 the whole square is also a second order factor. That's true. Now, when you equate that to 0, you will get s is equal to minus 2, meaning that this is a multiple pole, okay, sharing the same location. Okay, so this is a second order pole, but the feature is, but one of the nature of this is a real term. So real term, so that so this is a real term. So we have just proceeded like s plus 2 the whole square, and the magnitude that it offers is going to be minus 40 dB, which we have seen because of this factor, because right, minus 40 dB per decade. Okay, so that's what we we have seen. Now then when you consider the special case, same, I'm again considering a general open loop transfer function of the form k into 1 plus sta into 1 plus stb divided by s raised to n into 1 plus st1 into 1 plus st2. So up to this, we have seen a general transfer function like this. So we have identified four different terms: 1 plus st, 1 plus stb, s raised to n, 1 plus st2, and so on. Right. Now we have done this s plus 2 the whole square can be considered as a first order factor as well, isn't it? As a product of that, right? S plus 2 into s plus 2. So when you individually consider, each term will be offering a minus 20. Combining that you will get minus 40. So that is not a problem for us. Now, there can be a quadratic expression like this of the factor omega n square by s square plus 2 zeta omega n s plus omega n square. Now, when you factorize this, that factor or that root can be a complex in nature, right? Now, if that is the case, the procedure, there is a slight variation in the procedure. That's what we are going to consider in this session. Okay, so let us do that by an example, right? Say, for example, say if you have a g of s, h of s, something like this, 1 by s into half into s square plus 5s plus 6. So the first thing what you need to do is, when you encounter a quadratic expression like this, factorize that to see that whether it is real. You don't even need to factorize this. Just find out b square minus 4ac. This is a into s square plus bs plus c. So find out b square minus 4ac. If it is greater than or equal to 0, it's not a problem. It is simply a real quantity. So you may just find out the factors, and finding the factor s1 and s2, you can write this s squared plus 4 as s minus 5, s minus s minus s1 into s minus s2 form, right? So you can very well find out the Bode plot just as we have done previously by considering this as a two separate first order terms. Well, we'll move on to a problem. Now you're asked to find out, draw the Bode plot for the transfer function, apply the correction to the magnitude plot, and comment on the stability. So you're given with g of s, h of s, which is equal to 48 into s plus 10 divided by s into s plus 20 into s square plus 2.4 s plus 16. So far, when you identify the term, you have a constant part, you have a first order term s plus 10, say another term s, right? and 1 by s plus 20. Now this is a term which you haven't yet considered. Okay, even though this is a this is a quadratic term, right? But the thing is that since it is a real quantity, you can simply write as a first order factors, product of first order factors. Now, before going into that, the first step when you encounter a quadratic expression, the first step is find out b square minus 4ac of the quadratic equation. B square means b means 2.4, a means 1, c means 16. Now when you do this, you can see that this is less than 0. Now what does this value less than 0 means? This means that the roots are complex in nature. Okay, now if the roots are complex in nature, you should not go in this way, that is finding out those roots, and you can write like this as, and you can convert that into first order terms. Okay, so you don't need that. The thing is that if you find the factors or the roots to be complex in nature, what you need to do is you need to get a form, convert this into this form, omega n square by s square plus 2 zeta omega n s plus omega n square. Okay, so this is of the s square plus 2.4s plus 16. Now if it is required to get converted to this form, what must be the additional thing that you need to do? What is omega n square in this expression? So when you compare this, so you have a square. Okay, comparing these two, so comparing s square plus 2.4s plus 16 with this term, you will be getting this 2 zeta omega n is equal to 2.4, while omega n square is 16, right? Now if you want to convert this factor in this form, what you need to do is you need to multiply and divide by 16. Am I right? So when you multiply and divide by 16, so I will be rewriting that as g of s h of s is equal to 48 into s plus 10 divided by s into s plus 20, right, into s square plus 2.4s plus 16, right, into 16 divided by 16, right? So no problem. So that means this has become, now this has become, okay, this has become of the form omega n square by s square plus 2 zeta omega n square, right? Now the next term is, so this is actually your open loop transfer function of a closed loop system. Now what you need to do is you need to find out the sinusoidal transfer function. Now how will you find out the sinusoidal transfer? Putting s is equal to j omega, so that you will get g of j omega, h of j omega as equal to 48 into j omega plus 10 into 16 divided by 16 into j omega into j omega plus 20 into, what is j omega? So okay, I will just substitute j omega square plus 2.4 j omega plus 16, right? Okay, now you can convert this into Bode form. Bode form means 1 plus, it has to be of the form 1 plus. So converting this into Bode form, okay, this is Bode form, this is sinusoidal transfer function. When you convert this into Bode form, what you need to do is 48 into, you can take this 10 outside, so that this becomes 1 plus j omega divided by 10 means into 0.1, right, divided by 16 into j omega into, you can take 20 outside, right, 20 outside, so that this becomes 1 plus j omega into 0.05, right, 0.05 plus into what is the j omega square? J omega square is minus omega square. This is 16. So this is 16 minus omega square plus 2.4 j omega, right? Okay, and this into, don't forget to put the 16. Okay, right? Yes. Now, keeping the 16, you can simplify, or you can evaluate these terms, these constant terms. That is 40 into 10 divided by 16 into 20, but keep the 16 over here. Because we need a term omega n square by a square plus 2 zeta omega n plus omega n square. Okay, so this becomes 48 into 10 divided by 16 into 20 comes around to be 1.5 into 1 plus j omega into 0.1 into 16 divided by, so 16 minus omega square plus 2.4 j omega. So you need to keep this as a separate term. Okay, that will be nice. So into 16 divided by, so don't try to multiply this with the 16. That's a single term. Okay, a special quadratic term where the roots are complex in nature. Okay, so okay, so this will be j omega into 1 plus j omega 0.05. Okay. Okay, now coming to this, you can identify the terms. Okay, so first term is 1.5 by j omega. We know that this determines what? This determines the initial slope of the Bode plot. Slope of the Bode plot. Okay, and this is one, since it is 1 by j omega, it offers a minus 20 dB per decade. And one more information you will be getting, that this initial slope touches the 0 dB, or the 0 dB frequency is going to be equal to the value of k, right? It is equal to k itself, right? Why? Because the system is a type 1 system. Okay, right? So do remember the type 1 system, the 0 dB frequency will be equal to it will be equal to omega is equal to k. Okay, or you might be remembering this term, omega is equal to k raised to 1 by n. So since n is 1, omega is equal to k, here k is equal to 1.5. Okay, so this is a very important thing. If you want to find out the initial plot, you need to do all these manipulations. Otherwise, there is always a tendency to take 48. It's not 48, because initially in the question it is given as 48, but after converting it into Bode form, you will be coming into this 1.5. So you can say that this initially it having a slope of. Now what is the next term? Next term is you can say this term to be another term is, second term is 1 plus j omega into 0.1. Okay, so this is a term which offers a plus 20 dB per decade, right? Individually it offers a plus 20 dB per decade, which we have, the theory behind this already we have learned from the corner frequency omega c1. Let us put that as, what is the corner frequency? This will be 1 by 0.1, or it will be equal to 10 radians per second, right? Now what's the next term? The third term is 1 by 1 plus j omega into 0.05. So this also offers another plus 20. No, this offers a minus 20 dB per decade, because this is of the form 1 by. So this offers a minus 20 dB per decade, and there will be having a corner frequency that will be 1 by 0.05, or this is equal to 20 radians per second. Okay, so we have identified the three terms. Now, what is the fourth term? The fourth term is 16 divided by 16 minus omega square, okay, plus j into 2.4 omega, right? Now, we haven't yet seen how to deal with such a second order term. Okay, so now how to plot this, how to obtain the, now you want to find out two things. One is how much slope it offers. Okay, since it is a second order system and that too it is in the denominator, you can have a guess of that. That is, the guess is nothing but, since it is in the denominator and that too it's a second order system, this will be definitely offering a minus 40 dB per decade. But you need to prove it, whether you do want to know whether it is offering a minus 40 dB. And the second aspect is we want to know the corner frequency. I mean, in these two factors we can simply find out the corner frequency by taking the reciprocal of the term that comes along with j omega. So uh, now how will you find out in this case, how will you find out this term? Because we have an omega term at the two sides. So how will you find out that? For that, we'll be again considering a general second order term, and we will be doing the finding out the slope offered by that term, as well as what? As well as the corner frequency corresponding to such a second order term. So do remember, you must go in this approach only once you find out the factors or the roots to be imaginary. For that, you just need to test this b square minus 4ac. If it is less than 0, then you don't have to bother to find out the roots and so on. You may just proceed in this way. Now I'm going to explain how this, what slope this particular term offers to the Bode plot. So now for this, I'm going to consider a general term, omega n squared divided by, let's start with this, s squared plus 2 theta omega ns plus omega n squared. So this is a standard second order term. Okay, so you have studied when we dealt with the time domain analysis of a second order system. This is actually the transfer function of a second order system. This is of the form omega n squared by s squared plus 2 theta omega ns plus omega n squared. So based on this, we have found out this rise time, peak time, all those things, as well as in the frequency domain analysis also we have seen resonance peak, resonance frequency, cutoff frequency, and so on. Okay, so now let's consider the general transfer function of a second order system. Okay, so this is a term that we may encounter in such problems of, so it is not a must that it must be exactly of this form. This may be of this form. So you need to do the necessary change. That is, once if you get this this as a complex thing, then you need to convert this in this form, omega n square. So it is because of that reason. What is omega n square? I have just explained that. The omega n square is, okay, so here omega n square is 16, right? Omega n square is 16. So if you need to convert this into this form, you need to multiply and divide by that term. That's why we have done that. So make sure those two things. One is you need to identify whether it's complex. If it is complex, convert it into this form. Okay, it's very simple. Identify your omega n square from the s square term, from the quadratic expression, and divide and multiply that by that term. Okay, so if you have such a term, how will you find out the magnitude of this? Now the magnitude, now before going into the magnitude, you need to convert it into, so this is your GS, okay, this is your transfer function, okay, now okay, this is your transfer function, let us call this as T of S. Now you are to find out T of j omega. What is that? T of j omega means omega n square divided by, okay, j omega the whole square plus 2 theta omega n into j omega, right, plus omega n square, right? So this will be omega n square divided by, What is this j square? J square is minus 1. So this will be omega n square minus omega square, okay, plus 2 zeta omega n. So that is 2 zeta omega n omega. Okay, so that this can be written as omega n square 2 zeta by okay. Now this is expressing this d of j omega into decibel. How will you express this? This is nothing but 20 logarithm of what? 20 logarithm of this whole thing. Omega n square by omega n square minus omega square the whole, plus j into 2 zeta omega n omega, right? Now you can bring this down, omega n square, so that this becomes 1 by, so this will be 20 log of the magnitude, okay, 1 divided by omega n square minus omega square divided by omega n square plus j into 2 zeta omega n omega by omega n square, okay. So that this is equal to 20 log magnitude of 1 divided by, okay, so this can be written as 1 by omega n the whole square, right? This is 1 minus omega n the whole square plus j into 2 into zeta into, okay, this omega and 1 omega n cancelled, so this is 2 zeta into omega by omega n, okay. So you have converted this in of the form 1 by a plus jb form, okay. Now taking the magnitude of this, how to find out the magnitude of this? So look at this. So this is magnitude is 20 log of 1 divided by, this is of the form a plus jb, so this will be root of, okay, root of a square plus, so this can be written as root of 1 minus omega by omega n the omega n square the whole square plus 2 zeta omega by omega n the whole square, right? Okay, right, then you can bring this to the numerator side, so that this becomes 20 logarithm of root of 1 minus omega by omega n the whole square plus 4 zeta square omega by omega n the whole square, right? So this is it. So this is the expression for the magnitude of this quadratic term of the second order term, okay. Now let us see, just as we have seen in the first part of this Bode plot, how to find out the magnitude of such plots, okay. Now we need to know that so you know there is omega, right? Okay, now there is a term called as a omega n. What is this omega n? Omega n is the natural frequency of the system, okay. So you can have a comparison with the omega by omega n, or instead you can say that this omega by omega n can be much less than 1, or it is omega much less than omega n. That is, there is a natural frequency of the system, and the frequencies below, well below this natural frequency, what is its magnitude? The magnitude will be equal to minus 20 log, right? Now since this is much less than 1, omega by omega n is less than 1, what happens? The square will be much more less than this omega by omega n. Therefore, in comparison to 1, you can simply neglect this, right? So that becomes equal to, okay, so that becomes, now what about this? This is also for zeta square by omega n the all square. Now we are simply assuming that theta to be between 0 and 1, and this is also omega by omega n is also less than 1, means it is a fraction. So this fraction again into another fraction square becomes much more smaller than in comparison to this one. So this becomes 20 log 1. So that is 0 dB. So over this range, that is from omega up to omega n less than omega n, there will be a 0 dB magnitude. Okay. Now you can also find out the case. So this is case 1. Now let us see another case, the case 2, where omega by omega n is much higher than 1, or omega is much greater than your natural frequency. Then you can neglect this one, right? You can neglect this one, so that this becomes minus 20 log, right, root of minus omega n, omega by omega n the whole square, this minus, this one you can neglect, so that this becomes omega by omega n the whole raised to 4 plus 4 theta square omega by omega n the whole square, right? Now, as I mentioned to you that theta is assumed to be between less than 0 and 1. So that means, what can you say about this term? So omega by omega n is much greater than 1, therefore you can neglect this as well. So this becomes 20 log omega by omega n the whole square, or this is equal to minus 40 log omega by omega n the whole square, or this is equal to minus 40 log omega, okay, this is not square, this is minus 40 log omega by omega n. Okay, minus 20 log omega by omega n the whole square, this 2 comes over here, so this becomes minus 40 log omega by omega n, or this is equal to minus 40 log omega plus 40 log omega n, right? Okay, so this is minus 40, this can be written as log omega minus log omega n, right? So this minus and minus, this becomes plus. So this is the, so look at this. So you have found out right, you have found out two different values for magnitude at two range of frequencies. That is, for the frequencies much less than the natural frequency, it was found out to be 0 dB. That is an approximated one. And as in the case 2, what we found out is, if the frequency is much greater than the natural frequency, we have got a term like this, or we have got a term like this. That means, if you can say that this omega by omega n, since it is this is the variable, natural frequency is a constant, so omega by omega n can also vary from 0 to infinity. As it varies from 0 to infinity, it covers each decades. So that means this is actually offering a minus 40 dB per decade, right? So this is a minus 40 dB per decade. So coming back to our problem, this term offers a minus 40 dB per decade. Okay. Now the next question is how to find out the corner frequency. So there must be a WC3. What is this corner frequency? Now coming to the corner frequency, how to find out the corner frequency? You might be remembering the corner frequency. So if you are to plot this graph, you can plot like this, right? Say for a particular omega, say if you plot this omega by omega n versus magnitude, what you can say that this will be 0 dB for a particular till n ratio of omega to omega n, and after this will be okay, this will be going down at a rate of minus 40 dB per decade. Okay, that means there is a point of intersection for this slope and this one at 0 dB. So that means this point is going to be 0 at a particular omega. That's what we're going to find. That is, this becomes equal to this one. Okay, that's what this suggests. So that means you can say that minus 40 log omega by omega n is equal to 0 dB, right? Or what you can say is log omega by omega n is equal to 0. That's the meaning of this. Or omega by omega n is equal to 1, or omega is equal to omega n. What is the meaning of this? This is the natural frequency. So the corner frequency of a second order term of the form omega n square by s square plus 2 zeta omega n s plus omega n square is omega n. So here this in our problem omega c3 is going to be your natural frequency. And what is the natural frequency? We have found out omega n square is 16. Do remember what you got is, from this is omega n square. Now if you want omega n, take the square of this. So what is your omega n? Omega n is equal to 4. That means this corner frequency of this term is 4 radians per second. Okay, right? Okay. Now let us come back to these terms. So you have 4 terms. That is, one is 1.5 by j omega, which gives you an initial slope. That slope touches at the 0 dB at k, and that value of that k is nothing but, what is that value of k? K is actually 1.5 in this example, right? This is 1.5. Now the second one is, second term is 1 plus j omega 0.1, which offers a 20 dB per decade plus, but at a corner frequency 10. And again you have 1 by 1 plus j omega 0.5, which offers a minus 20 dB per decade from the corner frequency 20 radians per second. While the second order term comes into play and it offers a minus 40 dB per decade at 4 radians per second. Okay, now you can have a rearrangement of this in the ascending order of the corner frequency. So which among these 3 terms, this will be having an initial slope. Okay, coming to these 3 terms, among this, which term will come first? This one will be coming first, because 4 radians per second, from 4 radians per second, this was initially. So you need to have an idea. So the first one, Bode plot always starts with the minus 20 dB per decade, right? Okay, so you can have a rough figure of this. Okay, so this is it. It will be having a minus 20 dB per decade. Okay, then at 4 radians per second, this is offering a minus 40 dB. So minus 40, already it's minus 20, so this has to go at minus 60 dB per decade. Okay, then after that comes the 10 radians per second, which is plus 20. So already it was minus 60, plus 20 means this will be minus 40 dB, right? And this will be going up to 20 radians per second. After 20 radians per second, you will be getting an additional minus 20. So it again comes back to this minus 60. Okay, so the Bode plot initially starts with minus 20 dB. Then comes this factor, giving a cumulative slope of minus 60. Then comes this is having a plus 20, so it gets subtracted. Thereby it comes back to minus 40 dB. And because of this minus 20 at 20 radians per second, so you can make use of that and find out the Bode plot. So you can draw by it yourself. Okay, this you know how to draw this. Fine. Okay, now look at this. I'm going to draw this transform these data into this Bode plot. So for that, I have selected this as usual, selected as a magnitude. So this is 0 dB plus 20 dB, this is plus 40 dB, this is plus 60 dB, and you have a minus 20 dB, minus 40, and minus 60. Anyway, we require this. We have found out that we require at some stage we require the 60 dB. Okay. Now another thing is that the frequency axis. How to mark the frequency axis? Okay. Now coming to this, you have you know that the minimum frequency is 1.5. Okay, that is the initial slope or the 0 dB frequency. That is the minimum frequency. Then comes the 4 radians. then comes 10, 20. So it will be always nice to start with 1 radians per second. So this is 1 radians per second. So that means this is 10 radians per second. So this will be 100 radians per second, and so on. Okay. So what I'm going to do is, so I'm going to draw the initial slope. We know that this is, since it is a type 1 system, it is equal to the value of k after value of k of the Bode form. Do remember, it is not this value. Okay, this 48, it is 1.5. It is the value of k from the Bode form. That is very, very important. So, and the frequency is equal to k raised to 1 pi n. Since it is a type 1 system, it is equal to k, so it is 1.5 radians per second. So how to draw the initial slope? You can draw a, you can, first of all, you need to find out this 1.5. This is your 1, that means this is 2 radians per second, right? If this is 1, this must be 2 radians. So this must be a midpoint in between, that becomes your 1.5. Okay, so this is 1 and 2, 3 up to 10. Okay, so you can find out that from this you can find out the 1.5. Till that 1.5, this will be having a minus 20 dB. So the Bode plot will be plotted as shown. Okay. Okay, so I have found out that point corresponding to 1.5 on the 0 dB axis. Now how to draw the 20 dB line passing through this point? So this is actually a minus 20 dB, right? This one is minus 20 dB. Why? Because this is a decade, and as it moves from this decade, this 20 dB falls at to 0 dB at this. So this line is going to have a slope of minus 20 dB. And if you can draw a parallel line like this, this line will also be a minus 20 dB, and you know how to draw those parallel diagrams. Okay, so that can be drawn as follows. Okay, you can draw the parallel lines like this as well. You can make use of these two set squares. You have 2 set squares, I think. So you can use this and drag. Okay, so drag this point. I'm going to check it again. So this is 20 dB, right? Okay, so using this, dragging this to this point, you can draw. Okay, so look at this. So this is having a slope of minus 20 dB per decade. Okay, so what I have drawn is, I have just used this line and I have drawn this line parallel to this. So when you bring this, you can see that this is a parallel line. Okay, right? So this is 20 dB, and it will be going till what? Till the next corner frequency is 4 radians per second. So till this point, so you need to mark that, and up to that you will be having a minus 20 dB, and after that you will be having the effect of that second order term. Okay, so this is shown as follows. Up to this 4 radians per second, so up to this 4 radians per second you should darken this line, and after this comes the 4 radians per second, and the 4 radians per second is corresponding to the second order term, which offers a slope of minus 40 dB, but it's already at a minus 20 dB. That means from this point onwards you need to draw a 60 minus 40 minus 20 dB per decade. So effectively this is going to be, so it's like this, right? So this is what I have shown, minus 20. So from this point onwards it has to, you need to draw a minus 60 dB. Now how to draw that? So you know that this is minus 60, right? This is minus 60. Okay, this is the point corresponding to minus 60. And what is this line? Okay, this line is actually minus 60 dB per decade. So you may just draw a parallel line like this. So that will be minus 60 dB per decade. Okay, now coming to this, I have drawn this as the 60 dB line. So this is minus, so this will be having a minus 60 dB per decade. Okay, this is having a minus 60 dB per decade slope, and this effect continues up to 10 radians per second, right? Now from this 10 radians per second, this is the numerator term, which offers a plus 20 dB. So as I have shown here, now after this 10 radians per second, this is offering a plus 20. Minus 60 plus 20 becomes a minus 40 dB per decade. So from this point onwards, that is, this is your 1 radians per second, 10 radians per second. So that means from this point onwards, this graph is going to move at a rate of minus 60 dB per decade. So that can be drawn as, so you may find out the 40 dB. 40 dB is very simple. So you can simply draw a line and draw the parallel line like this. So this will be having a minus 40 dB per decade. Okay. So you will be getting this as minus 40 dB per decade. Okay. Till 20 radians per second, right? So when it comes to 20 radians, this also comes into play, which offers a minus 20 dB. So it comes back to this minus 60. So from this, how will you plot this minus 60? So you can draw a, okay, this is the line, okay, you can draw a parallel line like this. So this is going to be a minus 60 dB per decade. So this is actually your asymptotic Bode plot, right? And this needs a correction. Now how to correct such thing? That is the major difference between the problem which we have done previously. Now we'll see that. So anyway, the corner frequency is found out to be equal to the natural frequency, right? And this for a second order system, we have derived equation for the resonance peak. Okay, hope you are you may be remembering that. And the resonance peaks occurs at a value. Resonance peak occurs at a value as for theta. We have found out that theta to be in between 0.74, a value something like that. So as theta is in between this, there will be a resonance peak at the corner frequency or at the natural frequency. That's what we found out in the frequency response. So using that, we have derived a resonance peak in the frequency domain analysis. So I'll be writing the equation for you. The resonance peak which we have derived, so you may just look at that. So your peak resonance is given by MR is equal to 1 by 2 theta into root of 1 minus theta square, or this is equal to, this is in decibel, you can write this as 20 logarithm of this quantity, 1 by 2 theta into root of 1 minus theta square. Okay, now this is valid only for all these things we have found out. You may, if you have doubts, you may just refer those previous videos. So it is less than, till this theta point, there will be always a peak at the natural frequency, or at the frequency where omega by omega n becomes equal to 1, or omega is equal to the natural frequency. Okay, so this is what we found out there. So you may just go through that. You'll see that at this particular frequency there is a resonance of this, there is a resonance peak of this. Now since theta is in between this value, you can neglect this value, right? Okay, theta square becomes much more less than 1, so that this MR, the correction value, can be approximated to 1 by 2 theta. Okay, so you may find out the value of 1 by 2 theta for this graph. Okay, now how to find out that 1 by 2 theta, how to find out the theta? Now we know that 2 theta, so from this we know that 2 theta omega n is equal to what? So this is actually 2.4 s, right? S square 16 by s square plus omega n square by s square plus 2 theta omega ns plus 16. Omega n we found out to be 4 so that 2 zeta omega n is 2.4, or you can find your zeta as 2.4 divided by 2 into 4, which is 8, which is equal to 0.3. Okay, now what will be the correction? Now the correction response, or the response at that, will be 1 by 2 zeta, or the correction will be 1 by 2 into 0.3. okay, 2 into 0.3, or it will be 2 into 0.3, right? But you need to express that in decibel, so you can find out that value 20 log 1 by 2 into 0.3. Okay, so that we can see that 20 logarithm of 1 by 2 zeta is equal to 20 logarithm of 1 by 2 into 0.3, that is 6, or 10 by 6, and you can find out to be, so you can find out to be 4.43 decibel. So this is plus 4.43 decibel. So that means at 4 radians per second. So this is your 4 radians per second. And what is the significance of 4 radians per second? That is your natural frequency, or that is the corner frequency of the second order term. So this has begun at this, but there was actually a plus 6 dB, a surge at this. So how will you calculate this 6 dB? One point is 2 dB each, right? So from this you can have a this is 1 dB, 2 dB, 3 dB, 4 dB. It comes around 4.8, so somewhere over here. Okay, so this is it. Now how to get the rest of the points? So you need to get 2 points, so you need to find out. So you have the magnitude. So from this, so you have the net equation. Say, look at this equation. This is 1.5 plus. Okay, so this is the equation for you. Now using this expression, okay, you can find out the magnitude of this, right? 1.5 into 1 plus root of 1 square plus omega into 0.1 square. This is root of this thing, 16, divided by, this is also root of this. And what is the magnitude of this? This is omega. So you can have the magnitude of that and substitute omega is equal to, so in that equation you can, just as we have seen in the previous correction, say find out the values for omega at is equal to 2 radians per second, and omega to be 8 radians per second. Okay, so you'll be getting a graph like this. I'm not doing that for you anyway. So you'll be getting a graph something like this. Okay, what does this suggest? So at a corner frequency there is a peak. Okay, so you may just find out and draw it accurately. So this is actually your corrected Bode plot. If it not been corrected, then we will have a corner frequency, a Bode plot like this. Okay, now what is next? Next is to find out the phase. So what is the phase angle? Phase angle, you will be able to get the phase angle by like this. So to find out, you have the phase factor for this. The phase of this is 0. The phase of this is 0. Now you will be getting the phase as tan inverse 0.1. This is minus 90, right? Okay, then this is tan inverse 0.05 omega, and this will be tan inverse 2.4 omega by 16 by minus omega square. So that phase angle, or angle G of j omega, angle G of j omega, h of j omega is equal to tan inverse 0.1 omega minus 90 minus tan inverse 0.05 omega minus tan inverse 2.4 omega by 16 minus omega square. Okay, so using this expression of, you can have an arbitrary values. So you may just follow what I am doing. So find out, obtain the tabular column, j of omega, h of omega. Okay, obtain the tabular column. So to find out some values for these omegas, say put 1, 4, 5, 10, 20 and 50. Okay, so when you plot this, when you have this, you will be getting an equation, value like 96.25. This is minus 169. Okay, you may do it by yourself. I'm just putting some values. This will be minus 204.3. This will be minus 235.6. This will be minus 244.6, and this will be minus 256.8. So you may note down this. You may just do it by yourself. That's nice for these values. And this is quite simple. So here you need to mark this as your minus 180 degree. So as always, this is minus 150, right? And this will be minus 120, right? Minus 150, minus 120. Okay, now, okay, and it goes on like that. And this will be 200 and minus 210, minus 240, okay, minus 240, and so on. Okay, so you may just this is your phase angle plot, and you may draw just as we have drawn in the previous problems. I'm not going to do it for you that. Anyway, you may do it, and you will be getting the graph as, okay. Now after plotting, you will be getting the phase crossover frequency, and you'll be getting this phase okay, so your gain margin, you'll be getting your gain margin as 5 dB, okay, and your phase margin as 75 degree. So both are positive, therefore the system is a stable system. So do remember, when you find out the gain margin, you need to find out from the corrected graph. So anyway, this phase crossover frequency comes in between 4 and 5. I don't know exactly what it is, so you may just draw this. This is just a rough figure, that's why. So anyway, it comes in between 4 and 5. So at the phase crossover frequency, you will get a gain on this corrected peak, not on this line. Okay, that's very important. So you'll be getting almost a value closer to minus 5 dB. So the negative of the negative 5 becomes plus 5 dB, and phase margin is going to be 75 degree. That means that is your, so both are positive, therefore the system is an stable system. Okay.